Welcome to This Explainer. Today, we are unpacking an absolutely massive topic. But listen, we're not just going to do some dry march through microchip history or sit here listing off technical specs. Instead, we're going to look at humanity's fascinating, centuries-long quest to basically reverse engineer our own minds. Because artificial intelligence isn't just one single invention, right? It's really this evolutionary succession of competing theories about how the brain actually works. So, how do we get from ancient myths of artificial beings to machines that can converse, paint, and write software code? Well, let's trace this incredible journey.
It all really hinges on one deceptively simple question proposed by the brilliant mathematician Alan Turing way back in 1950. Can machines think? Now, to really appreciate this, you kind of have to remember the era. In 1950, computers were still these massive, loud, room-sized calculators that used fragile vacuum tubes just to do basic math. So Turing's leap from a giant calculator to a thinking machine was literally mind-blowing for its time. Because before him, thinkers were just hopelessly tangled up in all these philosophical debates about the soul and the exact definition of consciousness.
But Turing brilliantly reframes the entire pursuit with a simple operational test. He basically proposed a party game, often called the imitation game, to completely bypass millennia of philosophical dead ends. He argued that, hey, instead of asking if a machine really thinks, we should just ask, can the machine behave indistinguishably from something that thinks? By focusing entirely on observable behavior, he established the enduring fault line of AI. I mean, from 1950 all the way to today, the entire field has been completely split down the middle, observable behavior on one side and internal subjective experience on the other.
So let's dive into part 1, the era of rules. To see how engineers first tried to tackle Turing's big challenge, we really have to look at the Dartmouth Summer Research Project in 1956. This is where luminaries like John McCarthy and Marvin Minsky gathered to turn the dream of simulated intelligence into a formal academic discipline. And this birthed what we call symbolic AI. The engineers at the time possessed this really remarkable sense of hubris, honestly. They genuinely believed human intelligence could be solved in a single summer just by writing enough if-then statements. They thought intelligence was fundamentally just about explicitly manipulating representations and logical rules. And, for a while, it actually seemed to work. They built these early marvels that could prove mathematical theorems and play chess. The thrilling takeaway seemed to be that human-level AI was just right around the corner.
But man, did they severely underestimate the messy complexity of the real world. This led to a fascinating realization known as Moravec's paradox. It turns out that high-level reasoning tasks, like defeating a grandmaster at chess or solving complex calculus, were essentially just simple math problems for a computer. But the things that a human toddler does completely effortlessly, stuff like basic perception, having common-sense physical interaction, or just confidently walking across a room to open a door, that was an absolute nightmare to program. See, human evolution spent millions of years perfecting our physical intuition, so it feels easy to us, but it is extraordinarily difficult to explicitly engineer with rigid rules.
And this brilliant realization triggered a pretty devastating cyclical pattern for the whole industry. We'd see these early successes that led to massive hype and sky-high expectations, which of course brought in heavy investment. But then, as we just saw with Moravec's paradox, they'd smash right into a wall of technical limitations. Because demonstrating intelligence in a highly controlled game of chess is vastly different than general, real-world intelligence. This recurring failure to meet expectations led to profound disappointment and these devastating funding collapses that people in the industry call AI winters. During these deep freezes in the 1970s and late 1980s, funding completely dried up, careers basically stalled out, and the term AI almost became a dirty word in computer science.
All right, moving on to part 2, learning from the data.
To finally break out of those freezing AI winters, the field desperately needed a profound paradigm shift. They had to totally abandon that exhausting old approach of manually writing endless lines of logical code to describe every single rule of the universe. Instead, they asked this radical new question: what if we just build an environment where the machine learns what the world is on its own, directly from examples? This major shift towards statistical learning and neural networks completely transformed the central engineering problem of AI. Instead of hand-coding every little concept, you simply feed the machine data and let it discover the statistical structure all by itself.
Now, this approach had actually been bubbling under the surface for decades, but it was just completely starved of the necessary resources. That all changed dramatically in 2012 when 4 crucial ingredients suddenly aligned perfectly:
We finally had massive amounts of digital data, vastly more powerful compute, specifically using GPUs adapted from the video game industry, multi-layered neural networks, and much better optimization techniques. This perfect storm culminated in the AlexNet moment, which was an unbelievable breakthrough in computer vision that basically ignited the modern deep learning revolution. The machine was no longer just manipulating symbols someone else wrote, it was finally constructing its own useful representations of our messy world.
Which brings us to part 3, the generative explosion and agents.
The modern era of AI is defined by just an absolute explosion in capabilities, and it all traces back to a massive breakthrough in 2017. Researchers invented a brand new neural network architecture called transformers, introducing what's known as attention-based processing. This completely changed the game. It became the absolute foundation for the large language models we all use today. Suddenly, natural language became our primary interface with machines, and this seamlessly unlocked the huge generative AI boom of the 2020s. Modern AI stopped merely classifying existing information, like just spotting a cat in a photo, and started generating entirely new outputs. From drafting essays and synthesizing stunning images, to composing audio, generating video, and even writing complex software code, AI became a very real, direct creative partner.
But here's the thing, we are not stopping at just generation. We are currently right in the middle of another massive shift, moving from linear computation to AI agents. Look at earlier models. You provided an input, the machine computed it, and it spit out an output. Just a simple answer. But in agentic AI, it operates in this continuous autonomous loop. It perceives its environment, reasons through a problem, decides on a course of action, acts on that decision, observes the result, and then adapts its next move based on what happened. We are literally watching the machine transition from a highly advanced calculator into an autonomous worker capable of navigating the world and pursuing complex, multi-step goals.
And that leads us to our final section, Part 4, the unanswered questions.
Yet, as these incredible capabilities just continue to explode, we really have to pause and ground ourselves for a second. The history of AI isn't just some clean story of technical triumphs. It comes with profound physical costs. It's so easy to just call it cloud computing and treat it like it's this virtual, weightless magic happening in the sky. But digital intelligence has a staggeringly heavy physical footprint. To make this work, it requires millions of specialized chips, giant data centers, and massive electricity grids. To give you a real sense of scale, a single conversational exchange with a modern generative AI can require wild amounts of water just to cool the servers, not to mention the immense energy demands it places on local power grids.
Furthermore, beyond the physical costs, there are significant real-world challenges with how these models actually learn. A fundamental rule of thumb in the field is that prediction does not equal justice. Because AI learns entirely from historical data, a model trained on flawed or unequal historical records can perfectly reproduce past prejudices without ever truly understanding the context of what it's doing. For example, a hiring algorithm might inadvertently learn to downgrade resumes based on a certain demographic simply because of historical hiring trends buried in the training data. A machine can be mathematically, perfectly statistically consistent while still participating in a totally unjust system. It's succeeding, but for entirely the wrong reasons.
And this brings us to a massive existential hurdle known as the alignment problem. As these systems become more autonomous and agentic, how in the world do we guarantee they reliably pursue goals that are actually compatible with human values? If an agentic AI is tasked with solving a really complex problem, how do we guarantee it doesn't choose a path that's highly efficient for its goal, but ultimately harmful to humanity? This exact question is causing deep, heated debates among the world's top researchers right now. They are wrestling with who should control this power, whether open-source models are genuinely safe, and whether a hypothetical superintelligence could even be reliably contained if we build it.
And honestly, this brilliantly brings us right back to Alan Turing's old dividing line one last time, behavior versus experience. We have systems today that exhibit absolutely incredible behavior, but do they experience anything? It's the famous Chinese room thought experiment brought to life. If a person sits in a closed room and perfectly follows a rule book to translate Chinese symbols without actually speaking a single word of the language, do they truly understand Chinese? When a large language model manipulates mathematical symbols to write a beautiful, moving poem, does it possess any internal subjective consciousness, or is it just sophisticated statistics?
Which leaves us with this final, profound question to consider. As we constantly rebuild and reinvent these machines, going from rigid logical rules to deep neural networks, from simple image classifiers to fully autonomous agents. If machines can flawlessly perform the functions of thinking, what are we actually measuring when we call something intelligent? The most fascinating takeaway from this entire explainer is that artificial intelligence is very much an unfinished story. In our centuries-long quest to build a machine that thinks, we are ultimately just trying to discover ourselves. Thanks so much for learning with me today. Let that question linger.